So up to now, we've seen how the explicit method sometimes has always has problems with stability. And this is because it excludes information that has bearing on the solution. So for example, if we had our grid, I'm just going to draw a few grid lines here. What I'm going to do is I'm going to shade in the dots, the nodes that have an effect on the solution according to the explicit scheme. So let's start off here and we work in this direction. And the nodes that I've left open according to the explicit scheme don't have any bearing on the solution, but in real life they actually do. There's some connection between these 2 points. So we're going to introduce a method that's called the implicit method, which is an attempt to try and overcome this. But it comes at a cost of complexity. Okay, so the implicit method states that the spatial derivative can be approximated at the time tn plus 1 in order to calculate the value for time step at n. And this means we cannot solve explicitly for the value at tn plus 1 in terms of tn, and therefore we must solve an entire set of a whole system of simultaneous equations. So essentially what I'm talking about is if we had a grid that looks something like this, okay, grid nodes I plus 1, and I minus 1. We obviously have our time dimension in the vertical, so that's tn plus 1. What we do is we look at the spatial dimensions at tn plus 1 and the time dimension at tn in order to get the time value at tn plus 1. Okay, but because we don't know initially what the spatial values are at tn plus 1, it means we have to solve an entire set of simultaneous equations. The reverse, obviously, the explicit scheme says that where we look at the spatial dimensions at time n to get the value at time tn plus 1. Okay, so let's just look at the implicit method in the spatial dimension. So day squared phi by day x squared can be approximated by phi I plus 1 n plus 1. So remember, we're looking at the spatial derivatives at time n plus 1 minus 2 phi I n plus 1 plus phi I minus 1 n plus 1, all divided by delta x squared. And the derivative with respect to time can be approximated phi I n plus 1 minus phi I of n divided by delta t. So now plugging these two back into our, for example, diffusion equation, that is day phi by day t is equal to some coefficient, day squared phi by day x squared, we end up with the following. So we have minus lambda phi I minus 1 n plus 1 plus 1 plus 2 lambda multiplied by phi I n plus 1 minus lambda phi I plus 1 n plus 1 equals phi I at n, and lambda is equal to k delta t over delta x squared. Okay, so what I'm saying is that if we had to look at the weights of our different functions we have, so this weight at node I at n plus 1 is 1 plus 2 lambda, phi at I plus 1 n plus 1 is just negative lambda, and phi I minus 1 n plus 1 is also negative lambda, and then phi I n is just 1. Okay, and now the boundary conditions, well, it's the same as before. So if we're Dirichlet boundary condition, we would set that phi is 0, n plus 1 equals some value at tn plus 1, plug it back into this equation to get to derive a solution for phi of I at time step n, and the same can be done for the derivative boundary conditions, day phi by day x, which we've seen before in the explicit method.